So in this part of the lecture, I will now deal with the activated sludge model number 1 in much more detail, because that is the commonly used model in practice. I will very briefly introduce you to history so that you know a little bit where it comes from, and then show you in much more detail how the model was developed and how the model is, why certain aspects are in it in the way they are in. In 1987, this activated sludge model was proposed at the conference, was for the first time introduced. And what you have to realize is that the model was made by a group of people who were all busy with modeling in their own way. And they gathered together and they said, now we should find a kind of consensus model. So if you look in ASM1, there are certain aspects which are based on the fact that some people had their own way of dealing with things. That's a consensus model. It's maybe not the best model, but it's a model where everybody could agree on as being, well, here we can all work with, this all fulfills what we think is going on in a wastewater treatment plant. So the model was based on previous models, mainly from South Africa and from the United States of America, from groups there. And one of the main advantages of making that model, because in principle if you look to the equations, the processes, stoichiometry, they were all in these previous models. There was mathematically maybe not really new. It's more the fact that now everybody was using one standard notation, one standard way of presenting the models. And you don't need, if you now write a paper about activated sludge modeling, you don't need to describe the model. You can just say we used ASM1, but we changed this and this and this. So that's always much more easy to write down, and then you also know what the differences are. It's easier. So and also the symbols. Everybody used the same symbols. So if you read the different paper, you don't need to figure out what this time the symbols mean. ASM1, as you can find in most of the commercial packages, is quite often a slight deviation from the real ASM1 as it's published. That's not always mentioned, but effectively there is a lot of dialect, you could say. Basic principle is all the time the same. There are some small variations in how to deal, for instance, with ammonification or with some things like the particulate, the nitrogen content of the particulate compounds and this kind of thing. They're effectively usually small aspects which were in the big model because there had to be some kind of consensus also. But then when people implement in commercial packages, sometimes they simplify things because they found it's not really useful to include it. And ammonification is a typical process because ammonification itself is maybe relevant in very high loaded processes, but in most nutrient removal processes, ammonification is just a very rapid process, so it's not really needed to put that in a kinetic rate. It happens. So if you have Kjell or nitrogen entering a treatment plant, if it's not inert COD, the ammonia is split off usually in a very quick way, and it's not really needed to describe that. You can just describe that it's happening. So after this introduction of ASM1, there have been newer models proposed. They are good. They are partly good for the discussion so that people can see there are different ways of dealing with them. Partly they also include phosphate removal, but that makes the model much more complex, and the principle of making the model is the same. But it takes too much to deal that in detail here. And activated sludge model number 1 is just the most general model up to now. Activated sludge number 3 and metabolism-based models, they are more consistent and they are also easier for automatic calibration, but they don't bring big advantage for the general usage. The main problem in modeling is also, and that I would like to emphasize really, it's much more difficult to get good data from a wastewater treatment plant than getting good model parameters. And people focus quite easily on all the model parameters, the Ks, the mu max, the yield coefficients. But getting the correct recirculation flow rate, or the correct recycle flow rate, is often very difficult to do, and often 10% deviation in that flow rate has much bigger impact on the model outcome than 10% variation in the maximum growth rate. So the difficulty is characterization of wastewater treatment plants. The model has been developed stepwise. You can have two approaches. You sit together in a big room with all kind of people who know something about wastewater treatment plant, and you make a long list of what all might go on in that treatment plant, and then you put everything together in the model. Well, if you do that, you're sure that you include a lot of things that are not relevant. So if you develop a model, start simple and look with a simple model, how does it describe the system, and then add on what is needed. And know very well what you want to do. For instance, Activate Sludge model number 1 is developed to describe the oxygen uptake rate in a proper way, so that you can design aeration, control aeration, to describe the sludge production in a proper way, because anyway, sludge production and oxygen uptake rate are coupled, so if you do one good, the other is also good. But you're also interested in the amount of sludge you produce. And it's set up to describe the nitrogen conversions in a proper way, so nitrification, denitrification, and nitrogen assimilation. But for instance, it's not built to describe very well how E. coli is removed from the wastewater. So pathogens are not included, but there's all kind of reasons why you could include it, but it's not done, so there's no description of it in it. These were the points which should be in it, and that's also how, of course, then it's looked upon during model development. And then, of course, you need an experimental system to compare your model to see whether it's descriptive or not. And that experimental system was a system which had been running by the group in University of Cape Town in South Africa. A relatively simple Activate Sludge system, which was fed with pre-settled influent, raw, so normal wastewater but pre-settled, was only fed during 12 hours per day, so say during daytime there was loading of the plant, and during nighttime there was no loading of the plant. The reactor had a volume of 6.7 liters. The flow rate was about 18 liters per day, which was treated. They measured the VSS content in the reactors of 1300, the COD content of the reactor of 2000, the solid retention time of 2.5 days, temperature of 20 degrees, and the incoming COD was about 570 milligram per liter, and the Kjeldahl nitrogen almost 50 milligram per liter. So this characterizes the system, and what you then of course want to describe is that in the end you get an MLVSS content in the reactors of around 1400 milligram VSS per liter, the correct oxygen uptake, and the correct N conversions. Now you can start with a very simple model, and this is probably the most simplest matrix you can make. Just aerobic growth. You have 3 compounds which are then involved. Because you have aerobic growth, it's taking up of substrate, it's taking up of oxygen, and it is production of biomass. So we have 3 relevant compounds, and we have 2 processes. We have aerobic growth process, and we need a process because we know that if we increase the solid retention time, that the amount of biomass will decrease. And that is done, in this case, by the lysis process. We could have used here also maintenance or endogenous decay. They all work in a certain way, but the choice has been made to use lysis. And lysis is nothing else as you have a cell, it dies and falls apart into substrate. It becomes substrate again and new cells grow on it. So you have, for the aerobic growth 3 stoichiometric factors. One is equal to 1. The other is the yield coefficient for the substrate. And then the oxygen follows from the COD balance. And for lysis, we also define 1. We consume biomass. And again, from the COD balance, the substrate production should be then plus 1. For both processes, we can define a rate. For the growth, it's just the maximum growth rate times the affinity of substrate times the biomass concentration, assuming here that oxygen will be always available in sufficient amounts. And the lysis process is just a kind of first order process. The biomass falls apart with a certain chance, called the rate constant for decay. And if you then multiply, say, this matrix with the process rate equation vector, you can make the conversion terms and include that in the mass balance, and you have a model for the plant. If you would rewrite this now in terms, if you have a yield which is 0.6 or 0.66 as a standard yield which is used in wastewater treatment, then 1 divided by 0.66 is 1.5. Oxygen is 0.5 and the biomass becomes 1, and you can see that the biomass, but the COD balance fits. Remember that here the oxygen is described as milligram oxygen per liter, and oxygen is negative COD, so the COD balance reads here minus 0.5, minus 1.5 plus 1 should be equal to 0, and that is also what is happening. And also for the lysis process, the COD balance will hold. We put that in a reactor model, and we can compare the respiration rate to the measured respiration rate. The line is in this case the model, the dots is the experiment, and you immediately see a little bit the advantage of just starting with a simple model, because you see that some parts of the dynamics are correct and some parts are not correct. You see that once feeding starts, after 2 hours, oxygen uptake rate increases, so that's correct, but it doesn't increase that much as in the simulation and not that momentaneous. There's a kind of step and then a slow increase after that. Also, if you stop feeding and the model immediately respiration falls back to baseline, but in reality there seems to be some effect afterwards. And you see a small drop, so there is something related by direct conversion of compounds in the wastewater, but obviously a part of the compounds in the wastewater are degraded more slow than other parts of the wastewater. So it gives you a suggestion that maybe we have to describe a part of it as more slowly degradable substrate. You also see that the lysis process, that the baseline on the left side, so the endogenous process, is reasonably well described because the level can easily be reached. So what we observe is that we have a too low oxygen uptake rate during feeding, but that oxygen uptake rate after the stopping of the feeding is also not correct. And if you look in a little bit more detail, then you will see that if you take the total surface area between the model curve and the measured curve, that in both cases the total area is more or less the same. And that will indicate, because that area is the gram of oxygen per square meter per day multiplied by the day, so it's just a gram of oxygen consumed per cubic meter of reactor. And that area in both cases is the same, so the total amount of oxygen consumed seems to be okay. That's what you also can see from this curve. So then they had to come up with a solution, and that solution was to assume there are two types of substrate. From the respirometric behavior, for describing the oxygen, you obviously need two types of substrate. A slowly and a fast biodegradable process, and the slowly biodegradable material is converted to the fast biodegradable material by a kind of hydrolysis process. And the rationale behind it is that you probably have starch, proteins, polysaccharides. They cannot be degraded right away. They have to be split in small molecules, in small sugars and amino acids, and only then become available. And obviously this hydrolytic process is a slow process. So we can include that, which means we have an extra process and an extra substrate. And in Activate Sludge model number 1, that has then been taken as that slowly biodegradable substrate is also a particulate substrate. This is not necessarily true, but it's taken as such. You could also have making, well, a part is particulate and a part is soluble, but it has been proven that by assuming that it's slowly biodegradable material, we call it particulate, will work in the total model exercise. And to make the distinction between soluble and particulate is of course needed, because we need to know which compounds will settle in the clarifier and which compounds will just go out with the effluent. So we need an extra process and an extra compound. So if we add an extra compound, we have to realize what's happening with that compound in the other processes. Well, the slowly biodegradable compound, there's no direct growth on it, so it is not influencing growth. But by having this compound, we might now realize that in the lysis process, that if you have biomass, that it also first has to be hydrolyzed before it can be consumed by other bacteria. It's not, if the bacterium dies, it's not immediately sugars and amino acids, it takes some time to degrade it. So the lysis process we change. Instead of going from biomass to soluble substrate immediately, we convert the biomass into particulate substrate. So we have two types of particulate substrate. This which is derived from the influent, and this which is derived from the biomass decay. And some people group them together, as done in this graph here, and some people keep them separate in their models. That is one of the places where the models might deviate here and there. The net effect is not very big, whether you choose for one or the other. But then you have hydrolysis, and the hydrolysis just means the particulate or the slowly biodegradable COD is converted into easy biodegradable COD. And there is a bit more complicated expression, mathematical expression for it. It looks a little bit like a saturation term, but it's effectively a curve similar to the Langmuir isotherm. It's assumed that, say, the starch has to absorb to the biomass, and that is the rate limiting step. So, or the starch has to absorb to the enzyme, and that's the rate limiting step. And then you take a Langmuir type of isotherm, so an absorption isotherm, which has this form. So it's the amount of substrate per biomass, which is important, and not the substrate concentration as such. And again, you can see that all the COD balances on every line close. Put it in a mathematical expression, make a model out of it, and, well, the data points and the model line, they overlap quite well. So, for the oxygen dynamics, we could be satisfied. But we had a few more criteria on the model. Not only oxygen, but we started with oxygen. If we now, however, look to the measured TSS in the system, then we predict 1.6 gram per liter, although there was a measurement of 2 gram per liter. So obviously, we might predict the oxygen conversion well, we do not predict the sludge production well. Meaning, something is wrong. We forget something. And we have to increase the sludge production in one way or another. And then if we think about wastewater, then we can quite easily imagine that a part of the compounds inside the wastewater are not biodegradable. For instance, all the plastics, maybe even the cellulose which is in the wastewater is not easily biodegradable. All the hairs and nails which come down with the sewer are all non-biodegradable, at least non-biodegradable in the context of a wastewater treatment plant. It's only there for 10-15 days, and if it's not degraded in 10-15 days for a wastewater treatment plant, it means non-biodegradable. If you would have a year, it might have been biodegradable. So it's again within the context of the time frame you look to it. If you cut a tree, that tree is there after 1 year. You can say the tree is non-biodegradable, but if you wait 50, 60 years, it will be degraded. You'll see it slowly going away. So the term non-biodegradable you should see a little bit in context of the wastewater treatment plant. And for instance, in high-loaded systems, cellulose is hardly to not degraded, whereas in low-loaded systems with long solid retention times, cellulose gets quite well degraded, and there are more of these compounds. But we can introduce a new compound, non-biodegradable COD, because that will be not degraded and will lead to extra sludge production, because it's not oxidized. So in this case, we only add an extra term, the inerts. So there is a part of the wastewater COD is then assumed to be non-biodegradable. And we do something else, because that's also known that especially the cell walls of the microbial cells are very difficult to degrade. And they also accumulate in the sludge. So the content of the cell, that will be all converted, but especially the cell walls are very difficult to degrade. So if we have decaying cells, we say that about 90% becomes biodegradable and about 10%, or here effectively 8%, is non-biodegradable. Will accumulate also in the sludge. So you have again two types of inert matter. Inert, which comes in with the wastewater, and inert COD, which is produced in the decay process. The rest we can all leave the same, we assume, and the rate equations we also don't need to change, because we only added an extra compound, so different stoichiometry, not different rates. And it's also logical that we did not need to change the rates, because effectively the form of the OUR curve was described quite well. So if we implement the new model, now then we see that the measured oxygen uptake rate still has more or less the same profile as the simulated oxygen uptake rate, but suddenly we have a decreased total oxygen uptake rate. And that's logical, because the COD balance still holds, should hold. So we could have also anticipated this up front. When we increase the sludge production, we will decrease the oxygen consumption, or if we increase the sludge production, we will decrease the oxygen consumption. And that's what you exactly see here. And if you look to that, then we still see the correct dynamics of the oxygen uptake rate, but now there's not enough oxygen being taken up, which means that you have to go and think, well, maybe there's again another process which consumes oxygen. So what we observe with this model is that we have a correct trend of the oxygen uptake rate, we have a correct sludge production, but now we have a too low oxygen uptake rate. So the total is too low. And we need a process, if we look to the curve, which is slow, because all the day long, the amount of oxygen which is consumed by this other process is constant during more or less all the day, not depending too much on the influent. And of course we know a slow process in a wastewater treatment plant which consumes oxygen, that is the nitrification process. Adding the nitrification process means we have to add an extra organism, namely the nitrifying bacteria, but we have also to add two extra compounds, ammonia and nitrate, because ammonia is converted into nitrate. And then we have to, of course, evaluate again for each of these extra added compounds how they influence the already existing reactions. Now, ammonia is not only used in nitrification, but is also used for cell growth. So we have to add a stoichiometry factor for ammonia in the growth relation. And if the biomass contains 8% of ammonia, then that factor becomes 0.08. So at the lysis process, we also have to think about what's happening with nitrogen. And we assume that the nitrogen remains within the biomass. But then in the hydrolysis process, the slowly degradable substrate, for instance proteins, is degraded into amino acids, and then the ammonia is released again. So then the ammonia is set free again, and we have to produce, besides a unit of substrate, also 0.08 units of ammonia. So that's where also the composition matrix, or reminding what the composition of each compound is relevant, because you have to keep track of all your compounds. Now for the nitrification, there we have an amount of oxygen consumed, an amount of ammonia consumed, an amount of nitrate produced, and 1 unit per unit of biomass produced. It's again growth based. And you see that the amount of ammonia consumed is not exactly the amount of nitrate produced, again because ammonia is used for two things. It's used for energy generation in the nitrification process, and it's used as nitrogen source into the biomass. And you will see that the difference between ammonia and nitrate is again this 0.08, the nitrogen content of the biomass. So overall also the N balance in this case will fit. And because that's 4.25 should be equal to 4.17 plus 0.08 times 1. And that will nicely fit. In the lysis process for autotrophs, we assume again the same lysis process as for the heterotrophs. We just produce particulate substrate and a little bit of inert substrate. And then of course we need the rate equations, which are also in a very analogous way to the heterotrophic growth process, with the saturation terms for ammonia and oxygen in this case. And if you look to it, you will see that the COD balances will close, the nitrogen balances will close, and in this case there's no charge. But if we would have added the charge, it would have also been closing. We can run the model again, and we see again a description of the system, and we can see that the measured line and the modeled line are more or less identical. Again, not fully, but they are quite good. We can see also another interesting part from modeling, because by having a model available, we can immediately separate the total oxygen consumption into the oxygen consumption for ammonium oxidation and the oxygen consumption for the COD degradation. So we get an insight in where is the oxygen used and for which process. So we can do process analysis. Now, if you find this result, you have to wonder, is this sufficiently accurate enough? So can I live with this result? Because there is maybe 5 to 10% deviation in the oxygen uptake rate at say 1400 hours. And you can wonder whether that's important or not. Now, if you would measure oxygen uptake rates and your equipment has an inaccuracy of 5 to 10%, then it makes not much sense to make your model very much more accurate. If you are interested in this global trend and that's sufficient, you can deal with that, then don't make it more complex. But you could of course introduce also again slower conversions of ammonia so that you get a bit less during the feeding phase from 2 till 1400 hours and a bit more nitrification in the second part. It is what you want. It's both possible. But here it was decided not to improve, not to start to add extra compounds or extra processes, because that last part of the calibration can be done by just shifting some parameters. Moreover, also the nitrate concentration in the reactor was behaving well. During feeding, of course, the nitrate concentration drops because part of the nitrate is washed out in the effluent, and then once the feeding stops, the nitrate builds up again because nitrification goes on. Not all the ammonia is converted, and the ammonia line will be also well predicted, but then in the opposite way. So if we look to this model, then we find that we have a model which can correctly describe the OUR, correctly describe the sludge production, correctly describe the nitrification. This means that for our goal we can have a correct and good model, but this doesn't mean that we have our assumptions are correct. The assumptions we put in, they delivered as a mathematical description which is good enough for our purpose. And for instance, one of the assumptions we more or less did not make is we could have added, say, protozoa. A part of the particulate substrates and a part of the biomass will be degraded by protozoa. And we could have added an extra line describing the role of protozoa in the system. Well, since that does not bring really extra power and capacity to describe a wastewater treatment plant, despite their important role in a wastewater treatment plant, they have been left out. But this is one of the simplifying aspects, and this is also means that although the model can quite well describe the treatment plant, is very fit to do so, is accurate enough to do so, it does not mean that all the assumptions which are made are also true. You can do the reverse. If the model doesn't describe your data, you know the model is wrong. That statement you can make, but the opposite statement you cannot make. You have to, you can only state that the model is good enough for the purpose where you're going to use it for and where you have defined you want to use it for.